So let me just remind, we have particles evolving, say, in a one-dimensional torus. Okay, so you have to think that this is a one-dimensional torus with n points, and you have an exclusion rule which allows at most one particle per site, and so you have particles evolving on these set, which I called lambda n. And remember that E will stand for 1 over n. So I showed to you that this is a Markov process whose generator, which I'm representing by Ln, can be written as a sum from x in the set lambda n of f of sigma x plus e, eta minus f of eta. Okay, where, remember, sigma x plus e eta is just the configuration eta in which you exchange what happens at x and x plus e. Okay, you're all fine. So this is a process which we will study, and so my first observation is that, well, these dynamics conserve the total number of particles. Okay, so if you start with k particles, k between 0 and n, the total number of particles will remain the same in time. It doesn't change because you're just exchanging particles. Okay, I could create another dynamics which would not be conservative, but this one is conservative. It keeps the total number of particles. That clear? And what I claim is that, so let me call k the total number of particles. So this quantity is conserved. So the state space is not what I represented by omega n, which is 0, 1 to the power lambda n, but it will be actually lambda nk, which is the eta in omega n, such that the total number of particles is equal to k. And what I claim is that if you consider this process in this state space, then it is irreducible. So the Markov process, eta t, is irreducible. Okay, so let me prove that. So I'm starting from a configuration. And what I want to show is that you can go from this configuration to any other configuration which has exactly the same number of particles. So here you have 4 particles. So what I claim is that you can go from this configuration to that configuration. And how do you prove that? Well, what I will do is that I will go from this configuration to a configuration at which, let's say, all particles are at 0 up to k minus 1 over n. Okay, there are k particles. So let me place all particles from at the position 0 up to the position k over n. So let me show that I can go from this configuration to this configuration, and then from this configuration to that one. And how do you go from this configuration to this configuration? Well, how this process evolves? You wait exponential times of rate 1 at each of these bonds. The bonds at which you have a particle and a neighboring site. Okay, so in this configuration, you have 1, 2, 3, 4, 5, 6, and 7 possible jumps, right? And, well, so what I will do, with the probability equal to 1 over 7, this random variable, this exponential random variable, will be the smallest one. And if it is the smallest one among all these 7, this means that I will exchange what happens here and here, so that I will move this particle, so the leftmost particle, to the left. Okay? So I keep doing that until this particle goes to 0. Then I go to the next one, and I assume that the smallest exponential random variable is the one at the left of this second particle. If this is the case, this means that this particle will jump to the left, and I keep doing that until this second particle occupies the second position, the position 1 over n, and so on. So in this way, I move all particles to this position 0 up to k minus 1 over n. And this has a positive probability, right? Because the probability of this event is the probability that, well, I have one exponential, which is the smallest of a certain finite number of exponentials, then a second exponential, which is the smallest among a finite number of exponentials, and so on. So this event has a positive probability. So with a positive probability, I can move from this configuration to this configuration, or if you wish, the discrete time Markov chain can go from this configuration to that configuration. All right, because we have seen that the discrete time Markov chain jumps from one configuration to a neighboring configuration with uniform probability. Okay, with the probability equal to 1 over the number of neighbors. So any allowed jump, it's positive, and therefore the discrete time Markov chain can go from this configuration to that, and from this one to that one. Okay? So do you agree that if I fix the total number of particles, then this is an irreducible Markov chain? Okay, so if it is an irreducible Markov chain, I know that there exists a unique stationary state. And so I will represent that by mu n k. N because there are n sides, k because there are k particles. So this will be the notation for the stationary state. And what I claim is that this is the uniform measure. So my claim is that mu n k of eta, it's equal to 1 divided by the total number of particles on this set. Okay, and how many configurations we have? Well, we have n sides, k particles, so we have n choose k configurations. And so how do I prove that? We have seen that in order to prove that some measure, probability measure, it's invariant, I have to show that mu n k L is equal to 0. Okay? But actually, what I will prove is that mu n k satisfies the detailed balance condition. Okay? So the detailed balance condition was telling me that, well, what I have to show is that mu n k of eta times the rate at which I jump from eta to psi, it's equal to mu n k psi times the rate at which I jump from psi to eta. Right? Fine. But in order to prove, therefore, that this identity holds, since mu is uniform, what I have to show is that R, the rate jump, is symmetric. Okay, and what is the rate jump from eta to psi? Well, we have seen that this rate jump, it's either 1 if psi is an element of the neighborhood of eta, and it's 0 otherwise. Okay. But psi belongs to a neighborhood, to the neighborhood of eta, if and only if psi is obtained by eta by exchanging to a particle with a hole. So if and only if there exists x such that psi is equal to sigma x plus e eta. Okay? And x such that either, okay, there exists an x with this property in mind. Okay. No, this is not enough because if eta x is equal to eta x plus e, this configuration would be the same as eta. If you have two particles at x and x plus e, and if you exchange, you get the same thing, right? So for psi to be different from eta, I need eta x to be different from eta x plus e, right? So I need an x such that eta x is different from eta x plus e, and sigma will be equal to that. Okay? But if this is the case, okay, so what is the configuration psi? Psi is the same configuration of eta everywhere, but at x, and x plus e I exchange. So if I had a particle at x and an empty site at x plus e for eta, for psi that would change. And this happens if and only if eta is equal to sigma x plus e of psi. Okay? So if you have a configuration, then you exchange a hole and a particle, and you exchange it again, you go back to the same configuration. Okay? So if I apply sigma x plus e on both sides, I get here sigma x plus e psi, and here I get sigma x plus e eta, which is eta. Okay? So what we have shown is that this is equal to 1 if and only if there exists x such that eta x is different from eta x plus e, and psi is equal to sigma x plus e of eta. And this is if and only if there exists an x such that psi x is different from psi x plus e, and eta is equal to sigma x plus e of eta, and therefore if and only if r psi eta is equal to 1. Okay? So either psi is such a configuration, and therefore r is equal to 1. But if this is the case, r psi eta is also equal to 1. So this proves that r is symmetric. Do you agree? So r is symmetric, which proves that this measure mu, which is the uniform measure, is the unique stationary state. So this is what we prove. So we know exactly what are the stationary states. They are very simple. They are uniform. Okay? Fine. But now I want to study the thermodynamical limit. So I want to send n to infinity. So I want to consider this stationary state, mu and k. And we always will be interested in the limit as n tends to infinity. So I want to take this stationary state and send n to infinity. And then look at a very small neighborhood, say at a fixed number of sites, and to see what happens in this neighborhood. So since I'm here working with something which is translation invariance, I will look at these sites, let's say 0 up to L. So I'll fix this window. I will send n to infinity, and I'll fix my attention to this window. Okay? So let me say that I fix L, which is larger than 1, an integer. I will observe the sites 0, 1 over n, up to, say, L minus 1 over n. So I fix L sites. And let's say that I take a configuration zeta, which belongs to 0, 1 up to the power 1L, or 0L minus 1. So zeta will be a configuration zeta 0, zeta 1, up to zeta L minus 1. So it's a fixed sequence of zeros and ones. And my question will be, what is the probability that eta 0 is equal to zeta 0, eta 1 of eta e it's equal to zeta 1, eta L minus 1 times E, it's equal to zeta L minus 1. Okay, so I'm looking at the first L site, and I want to compute what is the probability that I observed exactly this configuration in the first L site. It's okay? And, well, but I'll send n to infinity. And of course, if I keep k fixed, I will have very large number of sites, a fixed number of particles, so these particles will disappear. If I look them at the first L sites, I will find no particles. Okay? So what I will do is I will keep the density, the total density fixed, which means that when I send n to infinity, I will send it together with the number of particles, k, in such a way that I keep the density. So k over n will converge to some alpha, where alpha is a fixed parameter between 0 and 1. Okay, so I fixed alpha between 0 and 1, which will be the density of particles. And I send n to infinity together with k in such a way that the density of particles, k over n, converge to this alpha. Right? And then I want to compute what happens on this finite window. So let's compute. Computation, it's very simple. So I want to compute this limit, and for that, let me call, so I have L sites, okay, so I fix the window of size L, and let me call M the total number of particles for the configuration zeta. So this is a sum from 0 up to L minus 1 of zeta j. So M is just the total number of particles for the configuration zeta. zeta, it's a configuration. It's an element from 0, 1 to 0, L. So zeta 0, it's either 0, 1. And I just sum, and I get M, where M, of course, it's a number between M and L. Okay. So if you want to compute this probability, well, you look at the first L site. So you fix the configuration in this L site. So if you want to compute mu, it's the uniform measure. So what the probability of this configuration, this event, it's the number of configurations which satisfy these conditions over the total number of configurations. Okay. The total number of configurations we know, so mu and k of all configurations such that eta 0 is equal to zeta 0 up to eta L minus 1 times E equal to zeta L. This is just, well, the total number of configuration we know it's n choose k. Okay, and how many configurations satisfy these conditions? Well, I have here m particles, and therefore L minus m holes. And here I still have n minus L sites. And in these n minus L sites, I have to choose k minus m sites to put particles. Okay. So the total number of configurations which satisfy these conditions is, well, I have n minus L sites and k minus m particles. Fine? So, what is this? So I have n factorial, and here k factorial, n minus k factorial, and over there n minus L factorial, k minus n factorial, n minus L minus k plus n factorial. So this is this ratio. And this is equal. So I have here n and here n minus L. So what I will get is n times n minus 1, n minus L plus 1. Okay, so this is the simplification of these two terms. Then I have here k factorial and k minus m. So that gives me k minus 1 up to k minus m plus 1. So these two. And then these two, I have n minus k and n minus, so let me write this as n minus k minus L minus m. And again, so I have n minus k, n minus k minus 1, up to n minus k minus L minus m plus 1. Fine? So how many, I have here L terms. Here I have M terms. And here I have L minus M. So I have the same number of terms in the numerator and the denominator. So what I'll do, let's divide by NL. So let me multiply and divide by n to the power L. Okay, if I divide, and now let me send n to infinity, but keeping the density equal to alpha. Okay? So if I divide by this expression by n to the power L, I have L terms, so I'm dividing each one by n. L is fixed, so this one will converge to 1, this one will converge to 1, and this one will converge to 1. So after this operation, the denominator will converge to 1. Okay? So now let's see the numerator. When I divided, so let me take m of these terms for the first and L minus m for the second. So when I divided by n, I'm dividing each one by n, and k over n, it's converging to alpha. So this one is converging to alpha. This one also to alpha. And since m is fixed, this one also to alpha. So I get here alpha to the power m. And for that one, if I divide it by n to the power L minus m, I get factor n for each of these terms. This one will converge to 1 minus alpha. This one to 1 minus alpha. And this one to 1 minus alpha. So I get 1 minus alpha L minus m. So this is the limit. Okay? So this converges to alpha to the power m, 1 minus alpha to the power L minus m. And this is exactly equal to, let me take mu alpha, a product measure of Bernoulli variables with density alpha. So this is exactly the probability that Z1 is equal, so that psi1 it's equal to zeta 1, or psi 0 it's equal to zeta 0, up to psi L minus 1 equal to zeta L minus 1. So this is mu alpha of all configuration psi such that. So what is this measure? This measure is what's called the Bernoulli product measure of density alpha. So this measure nu alpha, here we can define it, let's say that, let me define it in 0, 1 to the power z. So you take z, and at each point of z you place a particle, or you keep it empty. So the elements of z will be represented by psi. So psi, it's an infinite sequence. And so this is a probability measure on this space. And how do I characterize this measure? Well, under this measure, the variable psi x are independent. And they are identically distributed. And the probability that psi 0 is equal to 1, this is alpha. And the probability that psi 0 is equal to 0, it's 1 minus alpha. Okay, so this is a measure which is defined in the infinite space. And under this measure, these variables, so at each site you have independent variables, they are independent, and they are identically distributed, and the probability that the site it's occupied is alpha, the probability that it's empty, it's 1 minus alpha. So it's like that. You take a coin, and independently, this coin has probability alpha to give you a head. If you get a head, you just put a particle, and if not, you leave it empty, and you do that at each site, and in this way, you construct this infinite sequence. Okay? So these variables are independent, and they all have the same distribution. They take value 1 with probability alpha. So what I claim is that if nu alpha is this measure, then this object here, it's exactly equal to that probability. So let's compute that. Well, this is equal. The variables xi0, xi1, xil minus 1 are all independent. So the probability of this event, it's equal to the product from j from 0 to L minus 1, that nu alpha of xi j, it's equal to zeta j, because they are independent. Now, this product, let me now use the fact that these variables are all identically distributed. So this is equal to nu alpha. The probability that xi0 it's equal to zeta j. This is because they are all identically distributed. So they don't depend on these parameters. Now, what is the probability that xi0 takes the value zeta j? Well, this is equal to either alpha if zeta j is equal to 1, or 1 minus alpha if zeta j is equal to 0. Right? This is what I wrote here. I can write this expression as, well, this is alpha to the power zeta j times 1 minus alpha to the power 1 minus zeta j, right? Because if zeta j is 1, this is 1 and this is 0, I get alpha. If zeta j is 0, this is 0, so this is 1, this is 0, so I get 1 minus alpha. So let me write, so this probability, which is equal to that, it's equal to this. So let me replace this probability by the product g equal to 0 up to L minus 1 of alpha, zeta j, 1 minus alpha, 1 minus zeta j. And now what do I get? Well, it's a product, so it becomes a sum. And when I sum this expression, I get alpha to the sum of zeta j, but the sum of zeta j is m. So this is alpha to the power m, and 1 minus alpha to the sum of 1 minus zeta j, I get L minus m. So this is exactly what I obtained. Okay? So what is this telling me? This is telling me the following. If I take n very, very, very large, and I take the measure mu and k, so the stationary state, and if I look at a window, very small window, okay, here I fixed the size of the window, the same computation will show you that you can take this size as a function of n. But okay, I don't care. Take L is large but finite. So you look at that window, and what is the distribution of particles you observe? well, the distribution of particles you observe, it's exactly nu alpha. This is what we proved. Okay, if n is very, very large, the distribution of particles in this fixed window, it's very close because it converges to nu alpha. Okay. Questions about that? So that's computation, and this is the interpretation of the computation, which means that, well, if n is large, what you see is that these particles are essentially these sites. The distribution of particles in these sites are independent, and they have Bernoulli products. All right? Now I claim that these measures are also invariant. Okay? But there is a difference, because these measures, mu and k, they are concentrated on configurations with a fixed number of particles, k. While if I take nu alpha in this space, so if at each site I place a particle with probability alpha, and I leave that site empty with probability 1 minus alpha, and I do that independently, I get a measure on this space. This measure I claim, and I will show it's invariant, it's also invariant. But the difference is that now this measure, the total number of particles is not fixed, but it's a random variable. So this stationary state, it's not concentrated on configurations with a fixed number of particles, but concentrated on configurations whose total number of particles, it's a random variable, while these ones are not. These ones are concentrated on configurations with fixed number of particles. So taking the terminology from physics, these measures will be called the canonical measures, and these ones the grand canonical measures. Okay, in physics, so you have the micro-canonical stationary states, which are those which are concentrated on configurations with a fixed energy and a fixed momentum. Then you have the canonical ones, which are the ones which are concentrated on configuration with fixed momentum, but not a fixed energy. The energy may vary. And then the grand canonical, which are not concentrated, which do not fix energy or momentum. So taking this terminology, what we'll call as these ones are the canonical, while these ones are the grand canonical. So this is just names. But let me show that nu alpha is a stationary state. So I will represent by nu alpha n. So this is the measure on my space I raised on omega n. And how it is characterized, exactly in the same way as before. So under this measure, the variables eta 0, eta e, up to eta n minus 1 e are all independent and identically distributed. And the distribution is that the probability that I place a particle, it's alpha, which is equal to 1 minus the probability that I leave it empty. Right? So this is a new object, a measure, a probability measure on this space, and characterized by these two properties. Now, if I consider a configuration eta, I can write this as the sum for k up from 0 up to n of nu n alpha d configuration eta, given that the sum is equal to k, times the probability that the sum is equal to k. So let me compute So what is this probability? This is the probability of the intersection So that will be, well, if eta, the total number of particles for that configuration is not k, this is 0. And if the total number of configurations, the total number of particles is equal to k, this will be just nu alpha of eta divided by nu alpha of the sum. Okay. I'm computing this. This is the intersection divided by the sum. So I consider configuration eta, and I want also that the total number of particles is equal to k. If this configuration has k particles, so this is just the probability of that configuration. If this configuration has total number of particles which is different from k, the intersection is empty. Is that clear, or I'm using the same? Sorry? Is different. But otherwise, are you following? Okay, so now let me compute this ratio. Well, here I computed already. This is equal, I compute it over there. So this is alpha k, 1 minus alpha n minus k. Right? I've seen that. Now I know that the total number of particles is k, and I've seen that the probability of one configuration, eta, is just alpha to the total number of particles, 1 minus alpha to the total number of holes. So this is just what I wrote. So this is the numerator. And the denominator is the sum for all psi which are in nk of nu alpha n psi. Okay, so what is the probability that I have k particles? Well, sum of all configuration with k particles and the probability of each one. But the probability of this configuration will coincide with that, because psi has k particles and n minus k holes. And so this is just 1 over the total of. So what we just proved is that this measure is actually the uniform measure over all configurations with k particles. So what we just proved is that nu alpha n, So the measure I obtain when I condition that the total number of particles is equal to k, that this is equal to mu and k. All right? Compute the configuration of a zeta here. This is what we did, and we obtain that this is 1 over. Okay? That this measure, it's concentrated over all configurations with k particles, so it's 0 if you have a different number of particles. But if you have exactly k particles, this is exactly the uniform measure. Here I computed the conditional probability. So this is what I computed here, right? Because I'm computing the conditional probability, so I'm taking the intersection and dividing by this. So this is what we just computed, and what we proved is that if I condition the Bernoulli measure over configuration with a fixed number of particles, I get the uniform measure. Okay, so I started from the uniform, I send n to infinity, I obtain the Bernoulli. Now I take the Bernoulli, I condition on a fixed number of particles, I get the uniform. So I'm going back and forward. Or forward and back. Okay? So now let me go back to this equation. What I get is that nu n alpha of a configuration xi. So let me replace here eta by xi. So that this is equal to the sum of, well, this is the uniform measure. Mu n k xi times a weight, mu. So let me call that, this is a number, and this is.
Can you just cancel the weight in the right side?
Yeah, but I don't want. Yeah, I could, of course. I could cancel with this one with that one, but I don't want just to be able to write what I want to write now, which is nu alpha n So I concluded, so you see here, what you're computing is take the Bernoulli measure with probability density alpha, compute what is the probability that you'll get k particles. So this is a number which depends, let me call it C alpha. It's a number which depends on n and on k. Okay? So this is the probability that if you take a Bernoulli measure on n sides, you get k particles. For each k, it's a number. So, and if I sum over k, so they are all positive, and if I sum over k, I get 1. All right? So these, so C, what I call C n alpha k, it's positive, and if I sum from k from 0 to n, C alpha n k, this is 1. Fine. So if I replace this by that, what I get is that nu n alpha. So let me replace psi by a dot. That this is equal to the sum k equals 0 up to n, Cn alpha k, mu n k dot. So this is telling me that these Bernoulli measures are convex combination of these invariant measures. And so that these ones are invariant, okay, because they are convex combinations of invariant measures. And the difference is that this measure is now not anymore concentrated on configuration with a fixed number of particles. Okay, because, well, it will have k particles with that weight. All right? So this shows that indeed we have two families of stationary states. One which is indexed by k, the total number of particles, and this one, it's concentrated on configurations with k particles. So this is one family, the family of canonical measures. And then we have a second family of stationary states, which is indexed now by a continuous parameter, alpha, between 0 and 1. And this one, it's still stationary, but it's not concentrated anymore on configurations with a fixed number of particles. The total number of particles is now random. Okay? But we have two families. This is one family, and this is a second family. Right? Questions? Okay, so this is called the equivalence of ensembles. Yeah, sure. No, that will hold in general. So what's important here is that the dynamics is conservative. Okay? Take a dynamics which is conservative, the one you choose. Since it's conservative, it means that, and let's say that for each fixed number of particles, it's irreducible. So with these two assumptions, you know that for each fixed number of particles, k, you have a stationary state. Okay? So you have a family of stationary states, which here are the uniform, but for your dynamics, it would be something different. But what's for sure is that for each k, you have a stationary state. Now, you go to the thermodynamical limit. So you send n to infinity, keeping the density. That will converge. That will converge to a family which is now indexed by the density, because you are fixing the density to converge. So now you construct a second family of invariant measures. And they will be related by this relation. Okay? So you'll get if you have these two assumptions, what you get is, of course, here we compute it explicitly. It might be very complicated. I mean, it might be impossible to know explicitly what are the grand canonical measures. No. We just use the fact that it's conservative. right? But the picture you have to keep in mind is this one. If you take the canonical, then locally the canonical looks as the grand canonical. Fine. So now we are reaching situation in which, so as I said, this is called the equivalence of ensemble. So if you want to read more on that, in the appendix of my book, I talk about that. Equivalence of ensembles. So now I can start to consider this idea that we wanted. So I would like to define in my model a state, but which is not in equilibrium, but is locally in equilibrium. What do I mean by locally in equilibrium? It means that, well, I know that if I take the stationary state, I look locally, what I get is nu alpha, if the total density is alpha. Now, I fix a profile, rho. So rho, it's a, say, continuous function from the one-dimensional torus to 0, 1. So fix this function. So here is 0, and here is 1. And let's say that here is my density profile, which is not really continuous. So okay. So I fix a continuous function in the torus, and now I would like to introduce in my model a state which has the following property. If I look at a I fix a point x, and I look at a neighborhood Vx of this point x. This neighborhood, it's very small if I look at the interval 0, 1. So it should be very, very small, but sufficiently large to have many sides, to contain many sides. So it's something between 1 and 1 over n. Okay? 1, it's the total size. 1 over n, it's the size, the length of these intervals. So it's something between 1 and 1 over n, 1 over square root of n. Okay? So I look at this interval, and here, if I look at that interval, and I look at the distributions of particles on this interval, what I would like to have is to have a state which is very close to a stationary state. But which stationary state? Well, the one which has density rho of x. So I gave you this function. Now what I want is that if I look the particles around x, well, these particles are distributed according to a state which is very, very close to the state nu rho x. Okay, nu, it's the Bernoulli measure with density alpha. Now, rho, it's a function between, continuous function with taking values in 0, 1. So rho x, it's a number between 0 and 1. And I want the distribution in this neighborhood to be very close to this state. Okay. So I would like to introduce in my model these states, which I will call local equilibrium states. So So I have the equilibrium states, which are nu alpha or the uniform measure. But now I'm introducing the local equilibrium states. Local, why? Because, well, the equilibrium around x might be different from the equilibrium around y. Okay, because the density around x can be different of the density around y. Of course, if rho it's a flat, it's a constant function, then it's equilibrium. But if rho it's not constant, I would say that it's a local equilibrium. Okay, so given this function from the torus to 0, 1, and say that it's continuous, for the moment, I would say that mu n, so here, remember, I'm always sending n to infinity to have this idea of local equilibrium, sending n to infinity. So I would say that a sequence of probability measures, so mu n, it's a probability measure on my state space, which is omega n, which is 0, 1 to the power lambda n. I'll say that mu n, it's associated to the profile rho. So rho, it's a function. If for all continuous function, g, so g, it's a continuous function. So let me represent by Ct the set of continuous functions defined on the torus and taking values on R. Mu n, so I'll take the average, so the sum of gx, eta x, and I will compare that with the integral on the torus of gx rho x dx. Okay? And I want that to be larger than delta, and that the limit sup as n goes to infinity, that this is 0 for all g and for all delta. Okay, so this is you're averaging your configuration with a function g. So why I'm saying that this is more or less what we have here, so let me try to convince you. So assume that mu n, this sequence of measures mu n, satisfy this property. So assume that mu n has this property. Let me take 0, 1. Here is x. So I'll take the function g to be this function, very close to the step function at x minus epsilon and x plus epsilon. Okay, so here I'm requiring g to be continuous. Okay, so let me take a function which is continuous, but which is very close to this function, which is 1 between x minus epsilon and x plus epsilon, and which is 0 outside. Okay? So if I'm allowed to take this function here, which I'm not because I'm requiring g to be continuous, but let's forget that. What is this? Well, this is 1 over n, and I'm taking eta x for x between, so let me maybe call that z. X between z minus epsilon and z plus epsilon. Okay, so I'm counting the number of particles between z minus epsilon and z plus epsilon, and I'm dividing that by n. And what I'm saying is that this is very close to this integral, but g is 1, so this is the integral from z minus epsilon to z plus epsilon of rho x dx. So this is saying that, well, the average number of particles in this interval, the density of particles in this interval, it's very close to this one. In particular, if I divide that by 2 epsilon on both sides, I have exactly the density of particles. And what I'm saying is that the density of particles, it's very close to rho, it's continuous, so this is very close to rho of z. Okay. So this condition is telling me that for any z, I have, well, the density of particles around z, it's very close to rho of z. Okay, and then I would say that, well, the sequence of probability measure, it's associated to this density profile if that happens. And let me give you an example of a sequence of measure which is associated to that. So, questions about this definition? So let me give you an example. So rho, the density profile, it's fixed. Now, I will define a sequence of measures. So this sequence of measures, I will represent it by nu n rho. So this is a measure, a probability measure on my space 0, 1 to the power lambda n. So these are the configurations. Xi 0 up to xi n minus 1 times e. So how did I define this measure, nu alpha? I said, well, these variables are all independent, and they take the value 1 with probability alpha, and the value 0 with probability 1 minus alpha. So I will keep the first conditions. The variables xi x are independent. But now I don't want the density to be alpha. I want the density outside z to be rho of z. So I'll place a particle with probability rho of z at z. So the probability under this measure the probability that that psi of z will take the value 1, that will be rho of z. And this is 1 minus the probability that I leave that site empty. Okay, so I will put a particle at z with probability rho of z, and I will leave this site empty with probability 1 minus rho of z. And I do that independently at each site. It's like taking the coin, but now the coin, it's not homogeneous anymore. At each site, it has a different value of giving head. And now I claim that this measure satisfies this condition. So my claim is that nu n rho of the configuration eta such that 1 minus 1 over n sum over x eta x gx minus the integral on t of rho x gx dx, that this goes to 0 as n tends to infinity. Okay? So let me prove that. So I fix, so this is for all g, continuous function defined on the torus, and delta positive. So fix g and delta. And the first thing I claim is that I can replace this integral by the Riemannian sum. Okay, if I replace the integral by the Riemannian sum, the Riemannian sum is converging to the integral because these functions are continuous. And therefore, that will be smaller than delta over 2 for n sufficiently large. So it's enough to prove that by replacing this integral by this sum. Okay? If I can prove that this expression goes to 0, if replacing this integral by that sum, I can deduce that this expression converges to 0. Right? Because I will compare, I'll do a triangular inequality. I will compare that to that by comparing that to that and that to that. It's okay? Do you allow me to replace? Okay, so I replaced the integral by the sum. So this becomes this event, okay? The probability that this event it's larger than delta. So let me use Chebyshev inequality, saying that this is bounded with the square by 1 over delta square, the expectation with respect to nu n rho of the square of this expression. well, we have the square. So let's just compute this square. So this is equal to 1 over n squared. Well, I still have the delta square. The sum from x and y of the expectation eta x minus rho x, eta y minus rho y, gx, gy. Okay? Now, this is equal to 1 over delta square n square. Let me take the diagonal, so x equal to y. So x equal to y will give me gx square, the expectation of eta x minus rho x square. But eta x under this measure, it's a Bernoulli with density rho x. So this is the variance of a Bernoulli. So this is rho x 1 minus rho x. And then I'm taking the off-diagonal terms. But for the off-diagonal terms, these variables are independent. And so it's the expectation of eta x minus rho x times the expectation of eta y minus rho y. But rho x is just the expectation. These are 0. They are all 0. And so here I have n terms. So this is g, it's continuous, rho, it's continuous. So this is equal to 1 over delta divided by n times an expression which is converging to the integral of g square rho 1 minus rho. So this is of the order 1 over n. So it converges indeed to 0. So this proves that whatever continuous function rho you give me, this will be a sequence of measures which are associated to the continuous profile rho. All right? Questions? And now I can state my problem. I will start with a measure which is associated to a profile rho. So I'll start with a profile rho, continuous. And I will build a sequence of measure which is associated to this profile. And I will let time evolve. And what I expect is that at a later time t, what I will observe, it's a new profile. And that there is a PDE which describes how this profile evolves in time. So what I want to do, it's for the exclusion process, say, find the PDE which describes the evolution of the density profile in time. So that will be the goal. And in some sense, this so I'll present a technique which allows you to do that. And let's say that, as I mentioned before, the goal would be to start from molecules satisfying the Newton equation. And as the Newton equation conserved, say, mass, momentum, energy, or maybe start with a model which only conserves mass, and try to deduce how these molecules evolve macroscopically from the microscopic dynamics. So get what are called the Euler equations, or the Navier-Stokes equation for these gases starting from the microscopic dynamics. But this is, this is a very complicated problem. So what we did here is that we replaced these deterministic dynamics by a stochastic one. And by doing that, we are now able to derive these macroscopic evolution starting from the microscopic dynamics. So we described how these particles are evolving, they are exchanging position, and from these microscopic dynamics, we will derive the evolution of the density profile. So this will be the goal. So I prefer to stop here today so that tomorrow I will present you a model in which we can derive everything so that you'll have an idea of the timescales at which we have to observe these dynamics. And then Thursday we'll start, we come back to this model and start proving what we want. Okay, so let me stop here today.